Okay, now we're going to start talking about esters, which are once again very similar to carboxylic acids in the way that ketones are similar to aldehydes. So if we look at the difference between ketones and aldehydes, a ketone is surrounded by carbons. An aldehyde has a hydrogen at least one side. And if we compare that to carboxylic acids and esters, carboxylic acids have an OH on one side, whereas esters, that oxygen is now surrounded by another carbon. So esters are found in fats and oils, and they're responsible for aromas and flavors of bananas, oranges, and strawberries. So they're almost everywhere. You'll see them in a lot of places. And it's all about this oxygen double bonded to a carbon bonded to another oxygen. But notice that this oxygen is surrounded by carbons. So it's almost like an ether in a way. It's like an ether with a carboxyl acid attached to it. So they form this by esterification. Notice the word ester is in the beginning of the word. That's because we are forming an ester. Which is a combination of a carboxylic acid and an alcohol. And that becomes even more important when we start naming them, because you actually figure out what it was at the beginning before you name it. So I'll show. Here's a carboxylic acid. We have the oxygen bonded to an carbon bonded to an OH group. Then we have an alcohol. Here's your OH group here. What's happening is that the hydrogen and the OH are coming together to form water. In the process, this carbon and this oxygen are linking up, and that's where you get that carbon-oxygen bond. So in the process of esterification, you get water as a product, and you also get this ester as a product. When you're naming it, you're going to put a line through the two O's. You're going to name this side first and this side second. Sometimes it helps to say, okay, double bond is named second. So two bonds, name it second. Some people remember that by the 2 and the 2. So that means we named this part first. Well, this came from methanol. Or if you just want to look at the fact that there's one carbon there, we know that's methyl. That's meth. You name it as if it's a substituent. So it's like this is a substituent of all of this. So methyl is the first part of the word. Then we name this part over here. There's 2 carbons. So that's eth. Ordinarily it would be ethane. But we're going to drop the E and add O8. So methyl, ethyl, and O8. Ethyl methanoate. Here's another example. Here's the OH group and the H that come together to form water. This is your carboxylic acid and your alcohol. Then these two, the carbon and the oxygen, hook up right here. To name it, draw a line between the O's. The double bond means that you name it second, which means you name the side first. 1, 2, 3, that's propane. Because we're considering a substituent, it's going to be propyl. Now we name this side. 2 carbons means it's eth. Ordinarily it would be ethane, but we're going to change that E to an O8. So propyl ethanoate. Once again, these learning checks look like they're really confusing, but it'll be fine as long as you're able to break it down. So we're writing an equation for the reaction of propanoic. We know that prop is 3, so we have 3 carbons. Oic acid means it's a carboxylic acid. So that's one of our reactants. And methanol, we know that meth is 1. Ol means there's an OH group. So we're going to write the chemical reaction of these two things. Fill in the rest of them with hydrogens. Remember, each carbon gets 4 bonds total. So this has 4 bonds, 3 of which are hydrogen. This carbon has 4 bonds. This carbon had 4 bonds before we even added hydrogen, so it doesn't get any additional hydrogens. And we're reacting it with carbon and an OH bond. It only has 1 bond here from the OH, so that means I have to put in 3 more hydrogens. This OH and that H come together to form water. So that's going to be one of our products. And then this carbon and that oxygen are going to link up. So there's our 3 carbons from the propanoic. Now we have the oxygen going towards that methyl group. And we fill in the hydrogens. 4 bonds. This one's okay. This one already has 4 bonds, so we go to the next one, hydrogen. And then this one needs 4 bonds as well. We can take it one step further and name it. Draw the line between the oxygens. The double bond means we name that second. We name this side first. Name it as if it's a substituent, so it's methyl. This one has 3 carbons, so that's propane. But instead of saying propane, we're saying propanoate. And there you go, methylpropanoate. Alright, so some more practice with naming. We've already gone through these, so I'm not going to belabor it too much more. I will say, however, we did not talk about benzene. This is one way of drawing benzene. This is the other, with the alternating double bonds. Instead of benzene, it's benzoate. Alright, so let's name this one. First thing you want to do, draw a line between the oxygens. The double bond means that we name that one second, and then the other one first. 2 carbons, and we're going to treat it as if it's a substituent. So 2 carbons means F. Because it's a substituent, we're going to say ethyl. On the second part, there are 4 carbons here, so that's bute. It would ordinarily be butane, but we're going to drop the E. And we're going to add O8 instead. So ethyl, draw the line. Ethyl because there's 2. There's 4 carbons here, so it's bute. Right, drop the E and write O8. And it becomes ethyl butanoate. Okay, let's name this one. Draw a line between the oxygens. Double bond means second. You write the other one first. We have 3 carbons here. That becomes propyl. 2 carbons is ordinarily ethane. But instead of the E at the end, we're going to say O8 at the end. Propyl ethanoate. So propyl ethanoate. Acetate is the common name. Because this was originally considered acetic acid, which would have been memorized from the first section. Drop the E, the IC, and you add 8 instead. So let's take a look at some of the ways in which these are used. For instance, aspirin is an ester. Here's salicylic acid. The hydrogen here is then getting removed and putting this in its place. What they realized is that a salicylic acid would clear up a headache, but it would upset the stomach. However, if they combined it with an acetic acid and make it an ester instead, it actually didn't upset the stomach as much because you're not adding any more acid to the stomach. Then wintergreen is used for sore muscles, kind of like with icy hot. Alright, so draw the structure of the following compounds. So oic acid means it's a carboxylic acid. You'll notice that I always go backwards with these, so that way I know what I'm doing from the biggest chain first. So we know it's a carboxylic acid. Bute means there's 4 carbons. So carbon, 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 carbon. Carboxylic acid means that the last one is going to have a double bonded O and an OH. 3 bromo. Start counting from the oxygen. So 1, 2, 3, bromine. All the rest are filled in with hydrogens. This one already has 4 bonds, so I don't have to worry about that one. This one has 2 bonds, so I need 2 more. This one has 3 bonds, so I need 1 more hydrogen. And this one only has 1 bond, which means I need 3 hydrogens. Each carbon has 4 bonds. Ethyl propanoate. So O8 means it's an ester. Prop means that there are 3 carbons. And that's going to be the one with the double bond, because of the fact that it's written second. Then we're going to have another oxygen here, and on the other side of the oxygen we'll have an ethyl group. From here we just fill in the hydrogens. This carbon at the end only has 1 bond. That means we need 3 more, and those will all be hydrogens. This carbon has 2 bonds, which means we need 2 more. This oxygen has 2 bonds, which is fine. Carbon has 1, 2, 3, 4. We don't need any more hydrogens here. This carbon has 2. We need 2 more. And this carbon only has 1 bond, meaning we need 3 more. And here we go. The carboxylic acid. And on the 3rd carbon, there's a bromine. It's a ester. So here's our ester. First half has 3 carbons. Second half has 2 carbons. Okay, now, we were talking before about the combination of carboxylic acids and alcohols to create esters. Now we can actually reverse the process by adding in water. This is a catalyst. That just means that it's an acid catalyst. It needs something to speed up the reaction, and that hydrogen is what's going to be doing it. The water looks like this, HOH. So if you think of it in those terms, you might be able to see better that one of the hydrogens pop off and the OH goes one place and the H goes the other. So we are going to split right between the oxygens, just like we did when we were naming them. So that means the oxygen is right here at the end. This hydrogen goes towards that oxygen. That means we have an OH group sitting there, and that's going to get attached to the carbon. So we're essentially breaking this up when we add it with water, and it's going to form an OH and an H. So it's going to be 2 OHs here when you're done. Similar situation for the base hydrolysis. It's with a strong base. Think of this once again as an Na plus and an OH minus staying together. Notice in both scenarios, OH stays together. There's a couple different ways you can look at this. What's more than likely going to happen, however, is it's going to break off here, which is different than the previous one. The previous one broke between the oxygens. This one breaks after the oxygen. As a result, this oxygen comes over and takes away that sodium. And so we have the O and A here. And this OH group then comes over and attaches itself to that CH2. So here's your OH and Na, and they split up the bond. Notice the negative and the positive. That's very similar to how we had it with the carboxylic acid. In fact, this is a salt of a carboxylic acid. So that negative and positive is making it an ionic compound, which is then making it a salt. Because remember, an ionic compound, a salt is a generic name for any ionic compound. Alright, so let's look at some more ways in which these are used in real life. This is right here, this is the salt of a carboxylic acid. Because of this negative and positive. And how soaps actually work. Carbon and hydrogen are very close to one another in electronegativities, which makes them nonpolar. And if you remember from previously, like dissolves like. Which means a nonpolar compound is going to dissolve in a nonpolar compound, and a polar compound is going to dissolve in a polar compound. Well, the oil and dirt on our skin is also nonpolar. So what's happening is this tail, they call it the nonpolar tail, is reacting with the oils in our skin and the dirt in our skin. Or in this particular instance, I think that's supposed to be a motorcycle. And so it's actually combining with the oil. Oil and dirt. And then when you're done scrubbing, we have this polar end. They call it the polar head. Because this is an ionic compound, you have the positive and negative. You have an interaction with water. So that means that when you spray water on your dirty car, or when you splash water on your face after washing it with soap, this polar end is going to be attracted to that water, and as the water drips off, it's going to pull this chain off as the water comes off. So with this chain that's being pulled off, you're also pulling off the oil and dirt in your skin. And this is another explanation of how that happens. The nonpolar end dissolves the nonpolar fats and oils. And then when you rinse it with soap, the polar end then pulls away all the dirt and oil with the soap. Alright, so let's take a look at methyl acetate as it reacts with water and as it reacts with KOH. So let's break it down. Acetate means that it is an ester because of the ATE. Ace is also called ethanoate. And that's a memorization thing of knowing that ACET means 2. And this is the other part of it. So we have 2 parts. One is acetate, which has 2 carbons and a double bonded oxygen. The other part is the oxygen, and methyl means 1 carbon. We're going to react this with water and an acid catalyst, which means we have H plus on the top of that arrow. Because of this hydrogen and this H2O, we're going to sever this compound, and we're going to turn it back into the carboxylic acid it once was, and the methanol it once was. So carbon has to have 4 bonds. Here's 1 for the oxygen. It needs 3 more hydrogens. This has 4 bonds already. Fill in the hydrogens for this one. This one has 1 bond. It needs a total of 4, so we need 3 more hydrogens. This has 4 bonds, so it's okay. Give me just 1 second to get back to where I was. Okay. It needs 3 more bonds for the hydrogens. Now we're going to do the exact same thing, but now we're reacting it with potassium hydroxide instead. So we're using the exact same compound. We're breaking this compound apart, and we're reacting with KOH. So on one side, we have what would ordinarily be a carboxylic acid, but instead of that hydrogen there, now we have the potassium. And oxygen is a negative charge, potassium is a positive charge. And then this OH group then gets attached to the methyl group. So you retain that methanol. So those are the same. It's this that's going to be different because of it being a base. And there's your answers again. And that is the end of esters.